In this video, we're going to see examples of how a rock can depart from the linear isotropic elastic assumption. Actually, there is no rock which is linear elastic anisotropic. We just use this theory of linear elastic anisotropic as a good assumption because it helps us derive our equations and also write our problems in a very simple manner. However, rocks can be anisotropic, can develop plastic deformation, can also develop deformation with time, and can react also to changes in pore pressure and to changes in temperature. This is what we're going to see briefly in this video, and you should keep in mind the real rocks are not linear elastic and isotropic. We're just doing this simplification to make our life easier, but sometimes in real applications this might not be the right solution. The theory that we have shown before and we might see after, it might not be the right solution in order to approach a real rock, but it's good to get started. All right, so let's first talk about anisotropy. As we were saying before, rocks are seldomly isotropic. Most rocks, especially sedimentary rocks, they have strong anisotropy, which is caused by the lamination, which is caused by sedimentation of the rock and the sedimentation of layers and sequences in rocks of usually soft and stiff formations that may alter with each other. If you add to that fractures, you're going to have anisotropy. Probably is also in the horizontal direction, different from the vertical direction. In order to incorporate this anisotropy, what we do is to measure those stiffnesses in different directions and to summarize that into the stiffness matrix. Now this stiffness matrix is not dependent on just two parameters as we saw before, but for example for the orthotropic case depends on 9 independent parameters, and for the vertical transverse isotropic case depends on 5 independent parameters. So if we want to measure the properties of these rocks in the laboratory or in the field, we have to do additional measurements. Usually sedimentary rocks are stiffer in the horizontal direction than in the vertical direction. Here you can see an schematic about that, showing that because of the deposition of layers, usually sedimentary rocks are stiffer in the horizontal direction, and therefore the horizontal Young modulus is larger than the vertical Young modulus. And you may ask yourself the reason behind that, and that can be quickly exemplified with an Oreo cookie. Imagine an Oreo cookie. Well, you can see an Oreo cookie here, you don't have to imagine, but next time you before you eat an Oreo cookie, you press it in direction perpendicular to the cookie itself, to the plane of the cookie, and you will find out that what you're pressing is not, or what you're deforming actually, you're pressing both things, but you're deforming the filling, not the cookie. So the stiffness or the compressibility perpendicular to the plane of the cookie depends mostly on the filling and not on the cookie. And it's very similar with rocks. Now let's take the cookie here to this stack. When you have stacks of alternating soft and stiff layers, usually the vertical compressibility or stiffness, it's controlled mainly by the soft part. And that's what happens with shales too. And that's why the vertical Young modulus is usually lower than the horizontal Young modulus. As we were saying before, isotropy sometimes is not a good assumption, and you need to know when isotropy is not good. For example, for shales, for organic shales, isotropy is not a good assumption. You have to measure both the horizontal and the vertical Young modulus. As you can see in this title, there are some people that argue that even this could be a fatal assumption if you assume isotropy in shales. So just be careful about this. We'll come back to anisotropy later on when we talk about the strength of rocks, which is not the same as the stiffness, and we'll see that the rocks are also anisotropic regarding their strength. In here, we see that the elastic or the stiffness can develop anisotropy. So let's see an actual example about anisotropy. Here, this is a study of mine in which we measure horizontal Young modulus and vertical Young modulus for organic rich shales. And for example, here the shales in gray and black, you can see that clearly the horizontal Young modulus with field symbols is larger than the vertical Young modulus with the empty symbols. And for example, this other rock, it was an igneous rock and had a lot less anisotropy than the shale rocks. And you might ask yourself also, how much is a lot of anisotropy and how much is just not much anisotropy? Well, here I have another example, which is a compilation of data also for shales, in which we see that the ratio of the horizontal to the vertical Young modulus for some of these shales can be up to 4, while in some others can be not as much, close to 1. And that's usually linked to the composition of the shale and how much of those soft layers we have in between. The most soft layers we have in the sequence, the lower is going to be the vertical Young modulus and the more anisotropy I'm going to have. The less of those soft layers I have in the stack, the higher the vertical Young modulus is going to be and the more isotropic is going to be the rock. So for this ratio, something close higher than 2, we could say that is strongly anisotropic. Okay, we have seen then what is anisotropy. The next topic that we are going to see is, let's see what's next in the list, is permanent deformations. Rocks are not elastic. Many times they develop a permanent or a plastic deformation. A material which is elastic is a material that does not develop any irrecoverable deformation. On the other hand, we see that rocks all the time exhibit irrecoverable deformations. And an example of that is the data that you processed in your homework, in which you see that whenever we do a loading and then an unloading sequence after that, we see that this loading Young modulus is different than the unloading Young modulus. And the reason behind that is that when we load the rock, we usually also caused permanent deformations which are not recovered. If I had an elastic rock, like for example in this case, I would cause a deformation with loading, and if it is elastic, should come back the same way. However, this rock is not elastic, and instead of coming back the same way, it goes through a different path, which is this unloading path. And that is telling me right away that if I were to continue and decrease the axial stress, for example, in this case to 0, I would have an irrecoverable strain of more or less, in this example, of 1,000. And these irrecoverable deformations are going to make the rock, again, to be not elastic, and to develop these deformations that I have to take into account when I deal with problems in which the rock is not elastic. Further, let's try to see what happens if I continue loading this rock towards a maximum stress. Clearly, I can see here that if I break the rock, then this also is going to be an irrecoverable strain. And if I were to unload the rock from this point to zero axial stress, probably it's going to go back following my mouse over here, following a path like this, in which I'm going to have a significant irrecoverable strain. In many applications of geomechanics, we cannot ignore these irrecoverable strains, and we need to take them into account. In order to do that, we do have the theory of plasticity that we're not going to see in this course, but you should be aware of, and you should be aware of that many times in order to solve some real problems, you're going to have to include these irrecoverable strains. Let's see one other topic why rocks depart from what we assumed at the beginning: isotropic, elastic, and which one I'm missing? Isotropic, elastic, and linear. Okay, so next topic, it's time-dependent deformation. In the assumption of elasticity, we are also assuming that the deformation is independent of time, that we have almost an instantaneous response and a final state to every action that we apply. However, that's not true. In real rocks, sometimes the rocks take their time in order to react and to develop either a strain or a stress. And there are three typical manifestations of time-dependent deformation that usually are explained under the theory of viscoelasticity. Let me start with this one, which is probably the one that you know better. Whenever we impose a load onto a material, we would expect that as soon as we finish applying a load, we will see an instantaneous deformation. However, what we see with real materials is that even if we stop applying such a load, the material is going to continue to deform with time. This is what is called a creep strain. And the more time I let pass by, the more deformation I'm going to have, and this usually tends towards an asymptotic state. Here on the right, you see an actual example of that made with a rock tested in my laboratory, in which we load it to 500 psi, we hold the stress constant, and then we see that a deformation occurs nevertheless with time. We see the instantaneous response, but we also see the time-dependent deformation, which with a constant stress is called a creep strain. Let's now invert this process. Instead of keeping stress constant, we're going to keep strain constant. And this is this case. If we were to apply a controlled deformation on a rock, and then we stop applying that deformation, and we keep it constant, for example, let's say a compression, what we're going to observe is that there is going to be an instantaneous response of the rock, because it's not going to like to deform, it's going to oppose a reaction to that. And as soon as we keep the strain constant, the stress, for example, if this is a compression, is going to relax. It's not going to hold its initial value, but it's going to decrease with time, again, towards an asymptotic value. And sometimes this asymptotic value may be even equal to zero. For example, for salt rocks do not like to bear any deviatoric stress or any shear, and you may apply a shear instantly, but with time, the salt rock is not going to hold any shear, and eventually this is going to tend to zero. And this is what is called stress relaxation. And on the right, also, you can see an example about that, in which we subjected the same rock to a constant axial strain of more or less 3000, and then we keep it constant, and we see how the axial stress relaxes with time. Why? Because the rock is internally failing at a very small scale in order to accommodate that load, and it doesn't like to hold such a high load, but it's going to decrease that load with time because it's going to be failing internally. And this is what is called stress relaxation. And the last example is this example of fast and slow loading. And it's the same, or it's another manifestation of the same phenomenon, in which if you were to load a rock slowly, what you're going to do is you're going to accommodate all this internal failure slowly through time, so that the rock is not going to react so quickly to that, and the effective Young modulus that you're going to measure is going to be smaller than the one that you will measure if you load the rock very fast. Why? Because when you load it fast, the rock doesn't have the time in order to fail internally at a very small scale, and since it doesn't have the time, it's going to react with all its strength, and it's going to develop a higher Young modulus. Okay, so all of these can be explained under the theory of viscoelasticity. And let's see an application example about this. Let's see actually two application examples. One, I don't have a figure for this, but probably I can bring one up. I have the internet in here, so let me look for an image of a salt diapir, and let's look for a good one. And let's see. I think this is a good one. So what we see over here in this image, it's a apparently this is a shale diapir. Let's look for a salt diapir. Okay, this one is a good one. Salt diapirs are made of salt. This happens very often, for example, in the Gulf of Mexico, in which we have a body of salt which has a lower density than the sediments that were deposited after the salt was deposited. The salt is originally deposited flat, but then it rises because of its buoyancy, and it rises as a function of time. It might take several thousands or several tens or hundreds of thousands of years for this salt body to reach the surface, but eventually it does. Why? Because it developed this time-dependent deformation. If you wanted to drill a wellbore through these salt formations, after you drill the wellbore and you make a hole into the salt, you have to case your wellbore quickly enough such that the wellbore doesn't close on you, because as the salt tries to deform, it may close back onto the borehole that you did, and that's why you have to case it soon enough so it doesn't close. I have another example about this type of manifestation. Let me come back over here. We see that there are some formations like organic shales that are also viscoelastic and develop this time-dependent deformation. And if you remember, what we have seen from these elastic earth models is that the higher the tectonic strain we have, the higher the horizontal stress is going to be. And In some of these formations, if we initially, let's say that sometime during the Mesozoic, Mesozoic era, we had a high tectonic strain that caused a very high horizontal stress at a particular location. If we are in the presence of a viscoelastic formation, this stress is not going to hold for 100 million years, but it's going to relax with time to a lower value. Probably in the Mesozoic, it had a very high value, but with time, this value is going to decrease because of the time dependent or stress relaxation, in this case, of such stress. This will be the example for a reverse faulting case, and something similar occurs for the normal faulting case, in which, for example, if I had a formation that was formed in a basin such that I reach the minimum possible value of the minimum horizontal stress, if I have a formation that creeps with time such that it starts to push more and more sideways because it is deforming as a result of the vertical stress, this minimum horizontal stress might increase with time because of this viscoelastic deformation. And in this case, probably the term stress relaxation, it sounds counterintuitive because the stress is increasing, it's not relaxing. But what is really relaxing in this case is not the value of the horizontal stress, is rather the deviatoric stress, or the difference between the maximum and the minimum horizontal stress, which is the same as here. What it relaxes is the deviatoric stress, or the difference between maximum and minimum. And the same happens in this particular case. So, as a summary, remember that stresses do change with time. And sometimes they may change over the time of few hours, like in salts, which are very creepy rocks, or may take sometimes thousands or millions of years in the case of other less creepy rocks. Okay, the last topic we're going to see that we're going to see in order to understand a little bit better the real deformational response of rocks is the response that rocks have to pore pressure. We have seen that the deformation of a rock depends on effective stresses. The theory of pore elasticity goes a little bit further, and it postulates that the effective stress is not simply just the total stress minus the pore pressure, as what we have been doing so far, but also depends on what is called a Biot coefficient that depends on the compressibility of the rock as a bulk rock, but also the compressibility of the mineral. And what this is assuming is that also the grains within the rock can deform. And that deformation of the grains can cause an alteration on the relationship between effective stresses and strains. We're not going to see this theory in detail in this course. If you're interested about that, you can check my lectures in pore elasticity, my advanced geomechanics course. But you should be aware that this exists, and that in some cases, especially when you go to very high stresses, locations which are very deep, you may need this theory. And the last thing that we're going to see is that real rocks also develop strains and stresses caused by changes of temperature. And this is characterized by the coefficient of thermal dilation, which relates the change of length or strain due to a change of temperature. I think the example, which is in figure 327, is quite illustrative of the concept of a thermal stress. I guess you're all familiar with the thermal strain. You heat up something, very likely is going to dilate, is going to have a positive strain, at least in geomechanics, that's going to be positive. But probably you're less familiar with the concept of a thermal stress. Well, let's see this example. Imagine that now you have a solid that it is not allowed to deform in the vertical direction. If you heat it up, because it's not allowed to expand in the vertical direction, instead of dilating, it's going to develop a thermal stress. As long as these bottom and top boundaries, they are not moving. And that thermal stress is going to be a function of the change of temperature, of the change of the thermal dilation coefficient, and we can put that into our equations of elasticity and our constitutive equations by adding this term that takes into account the additional stress and the additional strain which is caused by a change in temperature. We're going to see how this applies later on when we talk about wellbore stability and also about fracturing. You will see that temperature can also cause stresses which are important in those two applications: stresses around wellbores and stresses around fractures. Okay, let me come back here to the table of contents and close with the same thing that I highlighted at the beginning. Rocks are not isotropic, rocks are not elastic, rocks are not linear. You need to be aware about that, and these topics that we have discussed in here go a little bit more in detail into taking into account all those things. For our course, we're just going to stay with the simple theory of linear isotropic elasticity, and we'll see how to solve problems with that, which is a very good starting for solving real and more complex problems.